Somewhere out there, a single star is pouring more light into the void every second than our sun will produce in an entire week. It is so blisteringly hot that it glows blue-white, so massive it bends the space around it, and so luminous it could outshine a million stars like ours combined. And yet, this titan is doomed. While our sun will burn steadily for 10 billion years, this monster will be gone in just a few million, a cosmic eye blink. It is racing toward a catastrophic death, and the very thing that makes it so dazzling is the same thing killing it. The brightest stars in all of creation are also the most desperate, the most violent, and the shortest lived. Tonight, we're going to find out why brilliance and doom are written into these stars from the moment they are born. Before we go any further, if you find this kind of cosmic deep dive fascinating, a quick like or subscribe really does help this little channel grow. It costs you nothing, but it means the world to me. Now, let's begin. Tonight, let's start with a number that almost doesn't feel real. Imagine a star shining with the brightness of more than 1,000,000 suns. Not 1,000, not 10,000, but over 1,000,000 of our own suns, all rolled into a single point of light, blazing in the dark. If you took such a star and placed it where our sun sits today, the Earth would not simply be too warm. It would be vaporized in an instant. The oceans boiled away. The rock melted and scattered into space before you even had time to notice the sky had changed. That is the kind of object we're dealing with. These stars are called blue hypergiants, and they sit at the very top of the cosmic hierarchy, the rarest and most extreme stars in the known universe. There may be only a handful of them in our entire galaxy at any given time, scattered like diamonds among the hundreds of billions of ordinary stars. And to understand what they are, we first have to understand what actually makes a star bright. Because here's the thing most people get wrong. When you imagine a brilliant star, you probably picture something enormous, something physically huge, and you assume that bigger simply means brighter. But that's not quite how stars work. Size matters, but it's not the engine. The real engine, the thing that determines whether a star whispers or roars, is the combination of two ingredients: mass and heat. Pile on enough mass, crank the central temperature high enough, and you get a furnace so violent that the light pouring out of it dwarfs everything around it. A blue hypergiant is what happens when nature pushes both of those dials almost as far as they can physically go. It is the most extreme answer to a simple question. How bright can a star possibly be before it tears itself apart? And as we'll discover, the answer to that question and the reason these stars die so young turn out to be the very same thing. Let's begin with the most obvious feature. The one hiding right there in the name. The color. When you look up at the night sky, the stars seem mostly white. But if you look carefully, you'll notice they come in different shades. Some have a warm, reddish-orange tint. Some are a creamy yellow-white, like our own sun. And a few, the rare and special ones, burn with a cold, brilliant blue-white light, like the tip of a welder's torch or the hottest part of a gas flame. That color is not decoration. It is the thermometer. The color of a star tells you, with remarkable precision, exactly how hot its surface is. And blue, it turns out, is the color of the hottest stars in existence. To understand why, think about a piece of metal heating up in a fire, or the coil of an electric stove. When it's cool, it gives off no visible light at all. As it warms, it begins to glow a dull, sullen red. Heat it more, and the red brightens to orange, then to a glowing yellow. Push it hotter still, and it shifts toward a brilliant white. And if you could somehow heat it far beyond what any stove or forge could manage, it would begin to glow blue. This is a fundamental property of how hot objects radiate light. Physicists call it thermal radiation, and the rule that governs it is sometimes named Wien's law. The hotter an object becomes, the shorter the wavelength of light it predominantly emits. Cooler objects emit longer, redder wavelengths. Hotter objects emit shorter, bluer ones. There is no escaping this relationship. It is woven into the physics of light itself. Now apply that to stars. Our sun has a surface temperature of about 5,500 degrees Celsius, or roughly 5,800 Kelvin, if we use the scale astronomers prefer. At that temperature, it glows a yellowish white, peaking in the part of the spectrum our eyes find most familiar. A cool red dwarf might have a surface temperature of only around 3,000 Kelvin, which is why it glows that deep, ember red. But a blue hypergiant, its surface can reach temperatures of 20,000, 30,000, even 40,000 Kelvin or more. That is not slightly hotter than our sun. That is 5, 6, 7 times hotter at the surface. At those staggering temperatures, the star's light is shoved so far toward the blue and ultraviolet end of the spectrum that it glows with that fierce, icy blue-white brilliance. So, when an astronomer sees a star burning blue, they know immediately without any further measurement that they are looking at something extraordinarily, almost violently hot. But here's where it gets interesting, and where we start to see why color and brightness are tied together. A hotter surface doesn't just change a star's color, it dramatically changes how much energy the surface radiates in the first place. There is a law in physics called the Stefan Boltzmann law, and it describes something that sounds almost unfair. The amount of energy radiated by a glowing surface doesn't increase in proportion to its temperature. It increases in proportion to the temperature raised to the fourth power. Let me say that again, because it's one of the most important ideas in this entire story. If you double the temperature of a surface, it doesn't radiate twice as much energy. It radiates 2 to the fourth power, which is 16 times as much energy. Triple the temperature and you get 3 to the fourth power, 81 times as much. Quadruple it, and a single patch of that surface blazes with 256 times the energy. So consider a blue hypergiant whose surface is, say, 7 times hotter than the sun's. 7 raised to the fourth power is 2,401, which means every single square meter of that star's surface is radiating roughly 2,400 times more energy than the same square meter on the surface of our sun. 2,400 times from the same amount of surface area. That is the brutal arithmetic of heat. And it explains something crucial. Even before we talk about how big these stars are, even before we mention their size at all, their sheer surface temperature already makes them ferociously, overwhelmingly luminous. The heat alone does most of the work. Now let's add the second ingredient back in, because a blue hypergiant is not only blisteringly hot, it is also enormous in mass and often impressive in size. But I want to be very careful here, because this is exactly the place where intuition leads people astray. Size and brightness are related, but size is not the cause. The cause is mass and temperature driving the rate of nuclear fusion deep in the star's core. The size, the luminosity, the color, these are all consequences, all symptoms of that furious central engine. Let me explain what I mean. Deep inside every star, including our sun, There is a core where the pressure and temperature are high enough to force atomic nuclei to slam together and fuse. Hydrogen fuses into helium, and in the process, a tiny fraction of the mass is converted directly into energy, following Einstein's famous relationship between mass and energy. That energy, born in the heart of the star, then claws its way outward over thousands of years, eventually escaping from the surface as the light we see. The brightness of a star, its true total energy output, which astronomers call its luminosity, is set by how fast fusion is happening in that core. A core that fuses gently and slowly produces a dim, long-lived star. A core that fuses with explosive ferocity produces a brilliant, short-lived one. And what determines the fusion rate? Above all else, it is mass. The more massive a star is, the more crushing weight its outer layers press down upon the core. That weight squeezes the core to higher pressures and far higher temperatures. And fusion is extraordinarily sensitive to temperature. A core that is even modestly hotter doesn't fuse a little faster. It fuses dramatically, catastrophically faster. So as you add mass to a star, you don't just add more fuel. You light that fuel on fire under far more extreme conditions, and the whole reaction accelerates wildly. This is the secret heart of everything we're exploring tonight, and we'll return to it in much greater depth. But for now, hold on to this single idea. Mass sets the temperature of the core, and the temperature of the core sets the rate of fusion, and the rate of fusion sets the brightness. Brightness flows from mass and heat. It does not flow from size alone. Once you understand this, the physical size of a blue hypergiant starts to make sense in a new way. A star fusing fuel at such a furious rate is pouring an immense torrent of energy outward through its layers, and that energy pushes back against gravity, inflating the star, puffing it up, swelling its outer envelope to tremendous proportions. So yes, many of these stars are physically gigantic, but the giant size is the star's response to its luminosity. The energy is generated first, in the core, and the swelling of the outer body is simply how the star reacts to carrying so much power through itself. So now we can finally assemble a proper definition of what a blue hypergiant actually is. It is, first, a star of enormous mass. Our sun has a certain mass that astronomers use as a convenient yardstick, and they measure other stars in multiples of it, calling these solar masses. An ordinary star like the sun is, by definition, one solar mass. A blue hypergiant might weigh in at 50, 80, or even 100 solar masses or more. We are talking about stars that contain the material of 100 suns, all compressed into a single object. That extreme mass is the foundation of everything else. Second, a blue hypergiant is extraordinarily hot at the surface, glowing that telltale blue-white as we've discussed, with surface temperatures often ranging from around 20,000 to 40,000 Kelvin or beyond. And third, flowing directly from the mass and heat, it is almost incomprehensibly luminous, often radiating hundreds of thousands to over 1,000,000 times the energy of our sun. That word hypergiant is reserved for the very brightest and most unstable of these objects, sitting at the absolute pinnacle of the luminosity scale, even above the merely supergiant stars. A hypergiant is not just bright, it is brushing up against the physical limit of how bright a star can be before its own light begins to destroy it, a limit we'll explore in detail later. Let me try to give you a feel for what these numbers actually mean, because raw figures like 1,000,000 times the sun's brightness can wash over you without landing. Picture our sun. It is, by any human measure, an object of unbelievable power. Every second, it converts something like 600 million tons of hydrogen into helium, releasing more energy in that 1 second than all of human civilization has produced in its entire history. It is the source of nearly all the light, warmth, and life on our planet. It is to us the very definition of overwhelming. Now imagine taking that sun and making it utterly insignificant. Imagine a star next to which the sun would be a faint, forgettable speck, lost in the glare like a candle held up beside a stadium floodlight. That is what a blue hypergiant is. If you replaced our sun with one of these monsters, the brightness in our sky would not increase by a comfortable amount. It would increase by a factor of hundreds of thousands or more. The light alone, never mind the heat, would be lethal. These are not stars that are a bit more impressive than the sun. They operate in an entirely different universe of power, one our minds genuinely struggle to picture. And these objects are not merely theoretical, they exist, scattered across our galaxy and others, and astronomers have studied a number of them in detail. Consider the famous reddish star Betelgeuse, which marks the shoulder of the constellation Orion. Now, Betelgeuse is not a blue hypergiant. It is a red supergiant, a cooler, swollen, aging star, and I mention it precisely because it makes a useful contrast. Betelgeuse glows red because its surface is relatively cool, even though it is enormous. It shows you that being huge does not automatically make a star blue, or even make it the most luminous kind. A blue hypergiant is a different beast entirely, hotter and more violently energetic at its core. For a true blue example, look at the bright blue-white star Rigel, also in Orion, gleaming at the hunter's foot. Rigel is a blue supergiant, a close cousin of the hypergiants, blazing with the light of tens of thousands of suns and burning with a hot blue surface. It is one of the most luminous stars easily visible to the naked eye. And when you look at it on a clear winter night, you are seeing that fierce blue heat directly with your own eyes, the light having traveled across an enormous gulf of space to reach you. Take the object buried near the heart of our galaxy that astronomers call the Pistol Star, named for the shape of the glowing cloud of gas it has thrown off around itself. It is wrapped so thickly in dust that not a single ray of its visible light reaches our eyes directly. And yet, when we measure the infrared radiation that does leak through that veil, we find a star pouring out the light of well over 1 million suns, packed with the mass of perhaps 25 or 30 suns crushed into one. It is so luminous that in a mere 20,000 years, it has expelled enough gas to build 10 ordinary stars. And that expelled gas is the pistol-shaped nebula we see glowing around it today. Now, travel beyond our own galaxy entirely, to a vast star-forming cloud in a neighboring galaxy, a churning nursery of newborn stars. At its center sits a cluster of monsters, and the greatest of them is catalogued with the unromantic name R136A1. This single star is among the most massive ever discovered, estimated to carry well over 150 times the mass of our sun, and it blazes with the light of several million suns. If you could somehow place it at the distance of our nearest stellar neighbor, it would be bright enough to cast shadows on the ground at night and to be plainly visible in broad daylight. It is, by some measures, the closest thing to an ultimate star that the universe has shown us. And then there is Eta Carinae, perhaps the most theatrical star in the entire sky, a colossal and desperately unstable hypergiant whose mass may exceed 100 suns, locked together in a fierce partnership with a smaller companion star. It is one of the most luminous stars in our galaxy and also one of the most volatile. A star that does not simply shine but visibly seethes and flickers, forever threatening to come apart. Astronomers watch it closely precisely because it sits so near the edge of destruction, a giant openly straining against its own power, one that may yet do something extraordinary within our own lifetimes. Each of these stars, the dust-cloaked Pistol Star, the titanic R13601, the convulsing Eta Carinae, sings the same song in a different key. Stupendous mass, searing heat, blinding light, and as we'll come to see, extreme instability and a shockingly brief life. These are not stars that settle into a long, comfortable middle age the way our sun has. They are caught from birth in a desperate, blazing sprint. Let me linger a little longer on why the color blue specifically signals such extremity, because it reveals something beautiful about how astronomers read the sky. When light from a star reaches us, we can split it apart into its component colors, the way a prism splits sunlight into a rainbow. This spread of colors is called a spectrum, and a star's spectrum is like a fingerprint. By examining exactly where the peak of a star's light falls within that rainbow, astronomers can determine its surface temperature with great accuracy without ever needing to travel there. A star whose light peaks in the red is cool. A star whose light peaks in the yellow-green, like our sun, is moderate. And a star whose light has been shoved all the way up into the blue and ultraviolet is searingly hot. What's striking is that the hottest blue stars actually emit much of their energy in the ultraviolet, in wavelengths our eyes cannot even see. So when you look at a blue hypergiant, the blue light you perceive is only a fraction of the total energy it's throwing out. A great deal of its output is invisible ultraviolet radiation, streaming outward unseen. This matters enormously because that flood of high energy radiation is part of what makes these stars so destructive to their surroundings and eventually to themselves. And they don't just shine, they blast their neighborhoods with energetic light, powerful enough to strip electrons from atoms across vast distances, lighting up entire nebulae of gas around them in glowing curtains of color. You might reasonably wonder how astronomers can claim to know the mass, the temperature, and the brightness of a star that sits thousands of light years away, a star no human will ever visit. The answer is one of the quiet triumphs of science, and it begins with light. Because a star's light carries within it a startling amount of information for anyone who knows how to read it. The temperature, as we've seen, comes from the color, from where in the rainbow the star's light peaks. But astronomers can go much further. When they spread a star's light into its full spectrum, they find it crossed by dark lines, gaps where specific colors have been absorbed by the atoms in the star's outer atmosphere. Each element leaves its own distinctive pattern of lines, a chemical signature, so that by reading those lines, an astronomer can determine not only how hot the star is, but what it is made of, and even how fast its surface is moving. And to find the true distance to nearby stars, astronomers use a method called parallax, watching how a star appears to shift its position ever so slightly against the background of more distant stars as the Earth travels from one side of its orbit to the other. Once you know the distance, you can convert the brightness you see in your telescope into the star's true total luminosity, the real power it pours out into space. When astronomers gathered all these measurements together for thousands upon thousands of stars and plotted them, Something beautiful emerged, a kind of map of all the stars in existence. This map is called the Hertzsprung-Russell diagram, after the two astronomers who developed it, and it is one of the most important tools in all of astronomy. On this map, the temperature of each star runs along one direction and its luminosity along the other. And when you place every star in its proper spot, they do not scatter randomly across the chart. Instead, they fall into clear bands and groups, revealing a hidden order in the heavens. Most stars, including our own sun, fall along a great diagonal band called the main sequence, the long, stable stretch of life during which a star fuses hydrogen in its core. And here is where the blue hypergiants reveal their extremity in the most visual way possible. They sit in the extreme upper corner of the map, the region of highest temperature and highest luminosity, far above and beyond nearly every other star. On this great chart of all stellar life, they occupy the very pinnacle, the loneliest and most rarefied territory, the corner reserved for the hottest, brightest, and most powerful stars that nature knows how to build. To find a star, that is to find a giant living at the absolute limit. I want to drive home one more time, because it is the very crux of everything. Why we keep insisting that brightness comes from mass and temperature rather than from size. Imagine two stars. The first is genuinely large in physical diameter but cool at the surface, the way an aging red giant can be. The second is more compact but ferociously hot. It is entirely possible for the smaller, hotter star to outshine the larger, cooler one, because that fourth power relationship between temperature and radiated energy is so punishingly steep. Each square meter of the hot star's surface is doing so much more work that even with less total surface area, it can win the brightness contest. Size helps, but heat dominates, and heat in turn comes from the mass-driven inferno in the core. So the chain of cause and effect runs in one clear direction. Mass first, then a crushed, super hot core, then a furious fusion rate, then enormous luminosity and a hot blue surface. Then, as a final consequence, an inflated, often gigantic body. The light is the cause of the size, not the other way around. This is the foundation we needed, and it sets up the central mystery beautifully. We now have a portrait of a blue hypergiant, a star of monstrous mass, surface temperatures that would make our sun look frigid by comparison, and a luminosity so vast that a million suns flicker like a single candle beside it. It is the brightest, hottest, most powerful kind of star that the universe knows how to make. By every measure of grandeur and energy, it stands supreme. And here is the paradox that should be nagging at you. The strange and almost cruel twist that we are going to spend the rest of our time unraveling. You would think that such a magnificent, powerful star, a star containing the material of 100 ordinary suns, would also be the most enduring. After all, it has so much more fuel. Our sun, with its single solar mass, will shine steadily for roughly 10 billion years. So surely a star with 100 times the mass, 100 times the fuel, should last 100 times as long, glowing for 1 trillion years, outliving everything around it. The reality is precisely the opposite, and it is one of the most counterintuitive facts in all of astronomy. These colossal blue hypergiants, for all their staggering reserves of fuel, are among the most short-lived stars in the entire cosmos. While our modest sun will burn on for 10 billion years, a blue hypergiant may exhaust itself in just a few million. In the grand sweep of cosmic time, that is barely an instant. If the life of our sun were compressed into a single human lifetime of 80 years, the entire life of a blue hypergiant, from its fiery birth to its violent death, would flash by in a matter of days. They are born, they blaze with unmatched glory, and they die, all in a cosmic heartbeat. How can this be? How can a star with vastly more fuel burn out vastly faster? How can having more lead to lasting less? The answer lies in that furious central engine we keep returning to, in the brutal mathematics of how fusion accelerates when you pile on mass and crank up the heat. The very qualities that make a blue hypergiant so dazzlingly bright, the extreme mass and the extreme core temperature, are the same qualities that doom it to a fleeting existence. Its brilliance and its brevity are not two separate facts. They are the same fact, seen from two different angles. The brightest stars in the universe must, by the unbreakable laws of physics, be the ones that burn out fastest. And in what follows, we're going to take that engine apart piece by piece, peer into the crushing heart of one of these giants, and discover exactly why a star that shines like a million suns is, at that very moment, racing headlong toward its own spectacular destruction. So we've arrived at the central paradox, and now we're going to crack it open. A blue hypergiant carries the fuel of 100 suns, yet it lives 100th as long, or even less. The answer to this riddle is hiding deep in the star's core, in the relationship between how much fuel a star has and how fast it chooses to spend it. And the word choose is the wrong word, really, because the star has no choice at all. The laws of physics make the decision for it the moment it forms. To understand why these magnificent stars burn out so fast, we have to descend, in our imagination, all the way down to the crushing furnace at a star's center and watch what actually happens when nuclei collide. Let's start with a simple way of thinking about a star's lifespan, because once you see it laid out plainly, the whole mystery begins to dissolve. The length of time a star can shine depends on two things, and only two things: how much fuel it has to burn, and how quickly it burns that fuel. That's it. It's exactly like a car driving across a continent. How far you can go depends on the size of your fuel tank and how heavily you press the accelerator. A car with an enormous tank that guzzles fuel at a reckless rate can easily run dry before a car with a small tank that sips fuel gently. The size of the tank alone tells you nothing. You have to know the rate of consumption too. Now, the amount of fuel a star has is, roughly speaking, proportional to its mass. A star with 100 times the mass of the sun has, give or take, about 100 times as much hydrogen fuel available in its core to burn. So far, this matches our naive intuition. More mass, more fuel, and if that were the whole story, the massive star really would live 100 times longer. But it is not the whole story, not even close, because the rate at which a star burns that fuel does not stay the same as you add mass. It explodes upward, and it explodes upward so violently, so disproportionately, that it completely overwhelms the larger fuel supply and then some. Here is the heart of it. The single most important relationship in this entire story. When astronomers measure how bright stars are compared to their masses, they find a startling pattern. A star's luminosity, its total rate of burning energy, does not rise in step with its mass. It rises far, far faster. For stars in the prime of their lives, luminosity scales with mass raised to a power of somewhere around 3 to 4. Let me translate that out of mathematics and into something you can feel. If you take a star and double its mass, you do not double its brightness. You increase its brightness by roughly 2 rays to the power of 3 or 4, which is somewhere between 8 and 16 times. Double the mass, and the star burns between 8 and 16 times faster. Now scale that up to the monsters we're talking about. Take a star with 10 times the mass of the Sun. Its fuel supply is about 10 times larger, but its rate of burning is something like 10 raised to the third or fourth power, which is 1,000 to 10,000 times the Sun's rate. Think about what that means for its lifespan. You divide the fuel by the burn rate to get the lifetime. 10 times the fuel divided by, let's say, 1,000 times the burn rate leaves you with a lifespan only about 1/100th as long as the Sun's. The extra fuel helped a little, but the monstrously higher burn rate crushed it utterly. The star drinks its vast reserves so recklessly that it empties the tank in a tiny fraction of the time, despite that tank being so much larger. And for the true blue hypergiants, the effect becomes almost absurd. A star of 100 solar masses has 100 times the fuel, yes, but its luminosity can be 1,000,000 times the Sun's or more. Divide 100 by 1,000,000, and you find the star lives only about 1/10,000th as long as our Sun. 10 billion years for the Sun, divided by 10,000, gives you 1,000,000 years for the hypergiant. The fuel barely matters anymore. The burn rate is everything. The star is so luminous that it incinerates its enormous fuel supply in what amounts to a cosmic flash. This is the resolution of our paradox in its purest form. More mass means more fuel, but more mass means catastrophically more burning, and the burning wins by an enormous margin. But this just pushes the question one level deeper, doesn't it? We've established that more massive stars burn vastly faster. The natural next question is why? Why should piling on mass cause such a wild, runaway increase in the rate of fusion? Why doesn't a bigger star just burn proportionally, calmly, in step with its size? To answer that, we have to go down into the core and understand the conditions under which fusion actually happens. Because fusion is a far more reluctant, far more temperamental process than most people imagine. Picture the core of a star. It is a place of unimaginable pressure and heat. A region where atoms have been stripped bare of their electrons, leaving a churning sea of naked atomic nuclei. The star wants to fuse these nuclei together, to slam hydrogen nuclei into one another hard enough that they stick and form helium, releasing energy in the process. But there is a tremendous obstacle in the way. Every atomic nucleus carries a positive electric charge, and as anyone who has played with magnets knows, like charges repel each other. The closer two positively charged nuclei get, the more ferociously they push apart. It's like trying to push the wrong ends of two powerful magnets together. The nearer you bring them, the harder they resist. For fusion to occur, two nuclei have to overcome this electric repulsion and get close enough that a different force, the strong nuclear force, can take over. The strong force is incredibly powerful, but it only operates across absurdly tiny distances. The nuclei have to be practically touching before they can grab hold and bind them together. So the entire challenge of fusion is getting two nuclei to approach close enough, fast enough, despite the furious electric wall pushing them apart. And the only way to do that is to make them move incredibly fast, to give them enough speed and energy that they can barrel through that wall of repulsion before it flings them back. Here we stumble onto a fascinating difference between a gentle star like our Sun and a furious giant like a blue hypergiant. A difference in the very recipe each one uses to fuse hydrogen into helium. They both turn hydrogen into helium, and they both release energy by doing so, but they take very different paths to get there, and that choice of path has enormous consequences. In a modest, cooler core star like the Sun, hydrogen fuses through a slow, patient sequence, sometimes called the proton-proton chain. In this process, individual hydrogen nuclei, which are simply lone protons, gradually find one another, stick together through a series of cautious steps, and slowly build up into helium. It is a sluggish, almost reluctant process, well suited to the relatively cool conditions in the Sun's core, and it is part of why our Sun burns so gently and lives so long. The proton-proton chain is the slow simmer of a quiet star. But in the searing core of a massive star, where temperatures climb far higher, a different and far more aggressive process takes over, called the carbon, nitrogen, and oxygen cycle. In this process, atoms of carbon, nitrogen, and oxygen already present in the star act as catalysts, as a kind of assembly line that grabs hold of passing hydrogen nuclei and rapidly stitches them together into helium before releasing the carbon to start all over again. The carbon is not consumed. It simply ferries the hydrogen through the reaction, again and again, like a tireless worker on a production line. And this assembly line is breathtakingly fast at high temperatures, far faster than the slow proton-proton chain. But it comes at a price, because this carbon, nitrogen, and oxygen cycle is even more savagely sensitive to temperature than the simmering process in the Sun. This is the very source of that monstrous temperature dependence we are about to explore. The reason a small rise in core temperature unleashes such a torrential surge in the rate of burning. Massive stars run on this furious cycle, and the cycle's extreme sensitivity to heat is precisely what makes their cores burn with such uncontrollable speed. So when we say that a hypergiant burns its fuel at a frantic pace, part of the reason is that it is using a fundamentally faster, hotter, more temperamental method of fusion than the patient one that keeps our Sun alive for 10 billion years. The Sun simmers. The hypergiant runs an inferno on an assembly line, and that assembly line speeds up wildly with every degree of added heat. And what determines how fast the nuclei are moving? Temperature. Temperature at the most fundamental level is simply a measure of how fast particles are jiggling and rushing about. In a hotter gas, the particles move faster. So in a hotter stellar core, the nuclei are slamming into each other at higher speeds, which means more of them can punch through the electric barrier and fuse. This is why temperature is the master controller of fusion. Raise the temperature even modestly, and you dramatically increase the number of nuclei moving fast enough to fuse. But here's the crucial subtlety, the thing that makes fusion so explosively sensitive to temperature. In any gas, the particles don't all move at the same speed. There's a spread, a distribution. Most particles move at moderate speeds, but a small number, way out at the extreme, move much faster than average. Fusion depends almost entirely on those rare, ultra-fast particles in the high-speed tail of the distribution, because only they have enough energy to overcome the repulsion. And when you raise the temperature, the number of particles way out in that extreme high-speed tail increases far faster than the average speed does. A small bump in temperature produces a large surge in the population of particles fast enough to fuse. The result is that the fusion rate in a stellar core is breathtakingly sensitive to temperature. For the kind of hydrogen fusion that powers massive stars, a process called the carbon, nitrogen, and oxygen cycle, the fusion rate scales with temperature raised to something like the 15th to the 18th power, or even higher. Let that sink in. Not the 4th power, like surface radiation we discussed earlier, the 15th or higher. That means if you increase the core temperature by just 10%, the fusion rate doesn't increase by 10%. It increases by a factor of 3 or 4. Double the core temperature and the fusion rate increases not twofold, but by a factor of tens of thousands. The core's appetite for fuel grows monstrously, explosively, with even small increases in temperature. Now we can finally connect all the pieces. We have a chain of cause and effect, each link forged by physics. Start with mass. A more massive star has more material in its outer layers, all of it pulled inward by gravity, all of it pressing down on the core. The more massive the star, the heavier this crushing weight, and the more the core is squeezed. That compression drives the core to higher pressure, and, critically, to higher temperature. A more massive star simply must have a hotter core, because gravity demands it. The core has to be hot enough, the pressure high enough, to push back against all that weight and prevent the star from collapsing. More mass on top means a hotter, more compressed center to hold it up. And then the temperature sensitivity of fusion takes over and amplifies everything. That hotter core, thanks to the 15th power relationship, fuses fuel at a wildly accelerated rate. So a modest increase in mass leads to a modestly hotter core, which leads through that brutal exponent to an enormously higher fusion rate, which means an enormously higher luminosity. The star pours out a torrent of energy, and because it's spending its fuel so recklessly fast, it empties its reserves in a flash. The mass causes the heat causes the runaway fusion causes the blinding brightness, and the blinding brightness guarantees a short life. Every link in that chain is forced. The star cannot opt out. The moment it forms with that much mass, its fate is sealed. There is one more feature of these massive stars that deepens the picture, and it concerns not just how fast the core burns, but how the star moves its fuel around. In our own sun, the core where fusion happens is relatively calm and still. Fuel that sits in the outer parts of the sun, away from the very center, can never reach the core to be burned. The sun, in effect, can only consume the hydrogen in its innermost heart, leaving most of its total hydrogen forever out of reach. It is a star that burns only a fraction of what it has. A blue hypergiant behaves differently. In the cores of these massive stars, the fusion is so ferociously concentrated and the energy so intense that the central region begins to churn and boil, like water roiling in a pot over a high flame. Great currents of hot material rise and fall, mixing the core thoroughly and constantly. Astronomers call this convection, and in a massive star, the convecting core is enormous, a vast turbulent churning region. This churning has a remarkable effect. It continually stirs fresh hydrogen fuel into the burning zone from the surrounding layers, feeding the furnace and ensuring it burns as completely and as fast as possible. So the hypergiant is not only burning hotter and faster than the sun, it is also stirring its fuel into the fire with brutal efficiency, dragging more and more material into the inferno rather than letting it sit idle on the sidelines. The star is, in a sense, doing everything it possibly can to consume itself as rapidly as the laws of physics will permit. It is hot, it is fast, and it is thoroughly, relentlessly mixed. Every aspect of its design conspires toward the same end, the swiftest possible expenditure of its enormous energy. And this is yet another reason why a star with 100 times the fuel can still burn out in a cosmic instant. It does not merely burn faster, it burns more completely, churning its reserves into the flames until there is nothing left to give. I find it helps to picture two contrasting stars side by side to really feel this. On one side, imagine a small red dwarf, a star with perhaps a tenth of the sun's mass. Its core is only modestly compressed, only modestly hot. Its fusion proceeds at a slow, gentle, miserly pace. It sips its hydrogen so frugally that it can shine, faintly but steadily, for trillions of years, far longer than the current age of the universe. In fact, not a single red dwarf that has ever formed has yet had time to die of old age, because the cosmos simply isn't old enough. These are the universe's marathon runners, pacing themselves so carefully that their fuel lasts almost forever. On the other side, imagine our blue hypergiant, 100 solar masses of material crushing down on a core heated to staggering extremes. Its fusion proceeds not at a gentle pace, but at a furious, frantic, all-out sprint. It dumps its entire vast fuel supply into the furnace as fast as the physics will allow, blazing with the light of 1,000,000 suns. And in doing so, it burns through everything in just a few million years. The red dwarf and the blue hypergiant are made of the same basic ingredient, hydrogen, fusing by the same basic principle. The only difference is the mass and the temperature. And that difference alone separates a lifespan of trillions of years from one of mere millions. A factor of 1,000,000 or more in lifetime, determined entirely by how hard the core is being squeezed. There is another way to think about this that I find deeply illuminating, and it has to do with efficiency, or rather, the lack of it. You might imagine that a star burning so brightly must be using its fuel with magnificent efficiency, but in a sense, the opposite is true. The hypergiant is being profoundly wasteful with time. It has the same fuel per unit mass as any other star, but it chooses, by virtue of its crushing gravity, to release that energy as fast as it possibly can. It's like the difference between a log smoldering slowly in a fireplace, giving off gentle warmth for hours, and the same log ground into fine sawdust and blown into the air, where it can ignite all at once in a brilliant, roaring flash. Same fuel, same total energy, but one releases it slowly over a long time, and the other releases it all at once in a burst of glory that's over in an instant. The hypergiant is the sawdust explosion. It cannot help but burn everything at once, because its core conditions force the fusion to run at maximum throttle. Let me put some real numbers to the lifespans, because they're genuinely staggering when you compare them directly. Our Sun, a one solar mass star, has a main fusion lifetime of about 10 billion years. A star of 10 solar masses, 10 times heavier, lives only about 30 million years, already 300 times shorter despite having 10 times the fuel. A star of 30 solar masses lives perhaps 5 or 6 million years. And the true monsters, the blue hypergiants of 80, 100, 120 solar masses, may live only 2 or 3 million years, sometimes even less. Pause on that comparison. The Sun has 10 billion years, the hypergiant gets 2 or 3 million. The most massive star, with 100 times more fuel, lives roughly 3,000 times shorter than the Sun. The arithmetic is merciless, and it all flows from that explosive sensitivity of fusion to temperature, and the way mass forces the core to ever greater heat. To appreciate just how brief these lives are, let's place them against the backdrop of cosmic history. Our galaxy, the Milky Way, is somewhere around 13 billion years old. In that vast span of time, Our sun, which is about 4.5 billion years old, is not even halfway through its life. It has watched over the Earth through the entire history of life, from the first single celled organisms to the rise of the dinosaurs to the appearance of humans, and it will continue burning for billions of years more. It is a creature of deep time, changing so slowly that across all of human history, it has barely aged at all. A blue hypergiant, by contrast, would have flickered into existence and snuffed itself out thousands of times over within the same span that our sun has quietly burned. If a blue hypergiant had been born at the same moment as our sun, 4.5 billion years ago, it would have lived and died completely within the first few million years. By the time the simplest life was getting started on Earth, that hypergiant would have been long dead for hundreds of millions of years already, its brilliant light extinguished, its remnants scattered. Every blue hypergiant we see in the sky today is, by cosmic standards, a newborn. It cannot be old. It is physically impossible for it to be old, because no star that bright can survive for long. When you spot one of these blue titans, you are looking at a star that was born, astronomically speaking, just moments ago, and that will be gone again almost as quickly. They are flashbulbs in the long, slow movie of the cosmos. This also explains something puzzling that you might have wondered about. Why are these stars so rare? Why are there only a handful of blue hypergiants in a galaxy of hundreds of billions of stars? Part of the answer is that very massive stars are simply uncommon to form in the first place. Nature produces far more small stars than large ones, but the bigger reason is their fleeting lifespans. Because they live for such an incredibly short time, at any given moment, only a tiny number of them exist. They are constantly being born and constantly dying, but each individual one is present for such a vanishingly brief window that you rarely catch one in the act. It's like trying to photograph fireflies in a vast dark field. There may be many sparks over the course of a whole night, but in any single instant, only a few are glowing. The blue hypergiants are the fireflies of the galaxy, each one flaring brilliantly for just a moment before going dark, replaced by new ones flaring elsewhere. Now, I want to add a layer of richness here, because the story of how a massive star burns is even more dramatic than just hydrogen fusing into helium. When the sun finally exhausts the hydrogen in its core, it will go through some changes, but it will never get hot enough to fuse the heaviest elements. A blue hypergiant is different. Because of its crushing gravity, when it runs out of one fuel, its core contracts and heats even further, until it can ignite the next fuel in the sequence. After hydrogen comes helium fusion, then carbon, then neon, oxygen, and finally silicon, each stage requiring a hotter core than the last, each stage burning faster than the last. And here the timescales become almost dizzying. A massive star might spend a few million years fusing hydrogen, the longest and most stable phase of its life. Then it spends perhaps a few 100,000 years fusing helium. Then the later stages accelerate terrifyingly. Carbon fusion might last only a few hundred or 1,000 years, neon fusion perhaps a year, oxygen fusion a matter of months, and the final stage, the fusion of silicon into iron, might last only a single day. Picture that. A star that has lived for millions of years, and in its final day, it is fusing silicon in its core in a desperate, doomed final act. Its lifespan now measured not in years, but in hours. The reason for this brutal acceleration is the same physics we've been discussing. Each successive fuel requires a hotter core to ignite. And at those higher temperatures, the reactions run faster and yield less energy, so they're consumed almost instantly. The star is racing down a staircase toward catastrophe, each step shorter and steeper than the last. This entire breathless sequence, this whole cascade of ever faster burning, is the direct consequence of the star's enormous mass and the punishing temperatures it creates. The same gravity that made the star so luminous in its prime is now driving it through these final stages at breakneck speed. Mass dictates the brilliance, and mass dictates the brevity, right down to that final, frantic day of silicon burning that sets the stage for the star's spectacular end. So let's gather up what we've learned so far, because it's the conceptual core of everything. The reason the brightest stars burn out fastest is not a coincidence or a quirk. It is forced by the deepest physics of how stars work. More massive stars have more fuel, but their crushing gravity heats their cores to far higher temperatures. And because the rate of fusion is so extraordinarily sensitive to temperature, rising with something like the 15th power, even a modest increase in core temperature unleashes a torrential, runaway increase in the rate of burning. The star's luminosity skyrockets, rising far faster than its fuel supply, with the result that the lifespan plummets. Brightness and brevity as bound together by an unbreakable chain. To be brilliant is to be doomed. The very fire that makes a blue hypergiant the most dazzling object in the galaxy is the same fire that consumes it in a cosmic instant. But we are not done, because there is yet another dimension to this story of self-destruction, one we have only hinted at so far. A blue hypergiant doesn't merely burn its fuel quickly. It is so luminous that its own light, the very radiation it produces, begins to physically tear the star apart from the outside. The brilliance doesn't just consume the fuel within, it blasts the star's outer layers off into space, stripping away its mass in colossal, stellar winds, making the star bleed itself into the dark. And as we'll discover next, the brilliance of a blue hypergiant does not only consume it from the inside. That same light reaches outward and begins to peel the star apart from its surface, so that the very radiance we admire turns into a force of destruction, a star so bright that its own light has become its enemy. So far, we've watched a blue hypergiant destroy itself from the inside, devouring its fuel in a furious rush because of the crushing heat at its core. But there is a second, equally astonishing form of self-destruction happening at the very same time, and it unfolds not in the hidden depths of the star, but right at its surface, out in the open, where the light escapes into space. A blue hypergiant is so luminous that its own light physically tears it apart. The radiation pouring out of it is so intense that it grabs the star's outer layers and hurls them away into the void, stripping the star of its mass at a rate that would seem impossible if we couldn't actually observe it happening. These stars do not simply shine, they bleed. They evaporate from the outside in, shedding the equivalent of entire planets every single year, blown off into the dark by the sheer force of their own brilliance. To understand how light can possibly tear a star apart, we first have to confront a fact that doesn't fit our everyday intuition. Light pushes on things. When sunlight falls on your skin, you feel its warmth, but you don't feel it shoving you, and so it seems absurd to imagine light having any physical force at all. Yet it does. Light carries momentum, and when it strikes an object or is absorbed by it, it transfers a tiny push. This is called radiation pressure, and it is very real. We see its effects in the tails of comets, which always stream away from the sun, blown back by the pressure of sunlight. We are even learning to use it deliberately in experimental spacecraft fitted with vast, gossamer thin sails designed to be pushed along by nothing but the pressure of light striking them. On Earth, with our gentle sunlight, this pressure is so feeble that we never notice it. But near a blue hypergiant, where the light is hundreds of thousands of times more intense, radiation pressure becomes a titanic force. Now think about what's happening at the surface of one of these stars. Below, in the core, fusion is generating a colossal flood of energy, an unimaginable torrent of light, clawing its way outward through the star's layers. By the time this radiation reaches the surface and streams off into space, it is so intense that it slams into the outermost gas of the star with tremendous force. The light is, quite literally, pushing on the star's own outer atmosphere from beneath, trying to lift it off and blow it away. And in a blue hypergiant, this outward push of radiation becomes so powerful that it begins to rival the inward pull of the star's own gravity. We have, in effect, a gigantic struggle taking place at the surface, gravity trying to hold the star together, and the star's own light trying to blast it apart. This sets up one of the most profound concepts in the study of these extreme stars, something called the Eddington limit. Here is the idea. Gravity holds a star together, pulling all its material inward. Radiation pressure, generated by the star's luminosity, pushes outward. For a normal star, gravity wins easily, and the star is stable. But as you make a star more and more luminous, the outward push of radiation grows stronger and stronger. The Eddington limit is the point of balance, the brightness at which the outward force of radiation exactly equals the inward force of gravity. If a star's luminosity ever exceeds this limit, then radiation pressure overpowers gravity, and the star can no longer hold onto its outer layers. They are simply blown off into space. Light wins. The star begins to come apart. And here is the breathtaking thing about blue hypergiants. They live right at the edge of this limit, sometimes brushing against it, sometimes even briefly exceeding it. They are so luminous that their own light is forever on the verge of overpowering their gravity. They are perpetually teetering on the brink of being torn apart by their own brilliance. This is not some rare malfunction, it is their permanent condition. A blue hypergiant exists in a state of constant, precarious near instability, always balanced on the knife's edge between holding together and flying apart. And this is precisely why hypergiants, as opposed to ordinary stars, are defined by their instability. They are so bright that they are barely able to remain stars at all. The most immediate consequence of living so close to the Eddington limit is the stellar wind. Every star has some kind of stellar wind, a steady outflow of particles streaming away from its surface. Our own sun has a solar wind, a gentle breeze of charged particles that flows out across the solar system and produces the auroras when it strikes the Earth's magnetic field. But the sun's wind is a feeble thing. Over its entire lifetime of billions of years, the sun will lose only a tiny fraction of its mass to this wind, barely worth mentioning. The wind of a blue hypergiant is something else entirely. It is not a breeze. It is a hurricane of unimaginable power, a gale of gas roaring off the star's surface at speeds of thousands of kilometers per second, carrying away staggering amounts of material. Let me try to give you a sense of the scale of this mass loss, because it is genuinely difficult to believe. Our sun loses, very roughly, a tiny sliver of its mass each year to the solar wind, an amount so small it's almost meaningless. A blue hypergiant can lose mass at a rate millions of times greater. In a single year, one of these stars might shed an amount of material equal to the mass of the entire Earth, blown off into space and gone forever. And over the course of just a few 100,000 years, a relatively short slice of even its brief life, a blue hypergiant might lose 10, 20, even 30 or more solar masses worth of material to its wind. Think about that. It can blow away the equivalent of dozens of suns, shedding more mass than most entire stars ever contain, all stripped away by the relentless pressure of its own light. The star is hemorrhaging itself into the cosmos. What's driving this wind so ferociously? It comes back to that flood of radiation, and specifically to how the light interacts with the atoms in the star's outer atmosphere. Remember that a blue hypergiant pours out enormous amounts of ultraviolet radiation, that high energy invisible light produced by its scorching surface. The atoms in the star's outer layers absorb this ultraviolet light extremely efficiently, and each time an atom absorbs a packet of light, it receives a tiny outward kick of momentum, a push. In the dense, brilliant radiation field of a hypergiant, the atoms are being struck and pushed millions upon millions of times, and all those countless tiny pushes add up into an overwhelming outward force. The light grabs the atoms and accelerates them outward, dragging them up and off the star and flinging them away into space. The wind is, quite literally, the star's atmosphere being blown off by the pressure of its own light, atom by atom, push by push. This kind of wind, driven by the absorption of light by atoms, is called a line-driven wind, because the atoms absorb light most strongly at specific colors or wavelengths that physicists call spectral lines. And the efficiency of this process is breathtaking. The more luminous the star, the stronger the radiation field, and the more powerfully it drives the wind. So once again, we find that luminosity is the master controller. The brighter the star, the more violently it strips itself. Extreme luminosity leads directly and inevitably to extreme mass loss. The two are bound together. A star cannot be this bright without also bleeding itself dry. The brilliance that makes it magnificent is the very thing that's tearing its outer body away. Now, here we arrive at a beautiful and important connection back to everything we've discussed. We've established that a blue hypergiant burns through its fuel catastrophically fast because of the runaway fusion in its core. And now we see it's also being stripped of its outer mass by its own radiation. These two processes are deeply linked, and together they conspire to seal the star's fate even faster than fuel consumption alone would. As the star blows away its outer layers, it's not just losing random material, it's losing the very envelope that defines it, peeling itself like an onion, exposing ever deeper, hotter layers to space. The star is being consumed from within by fusion and simultaneously stripped from without by radiation. It's fighting a war on two fronts, and it cannot win either one. Both processes are accelerated by its enormous luminosity, and both are racing it toward its end. The intensity of these winds and the instability of these stars produce some of the most dramatic behavior we observe anywhere in the cosmos. Many blue hypergiants don't lose mass in a smooth, steady trickle. Instead, they suffer violent eruptions, sudden convulsions, in which they blast off enormous quantities of material in a brief, explosive episode. These stars can flicker, brighten, and dim in unpredictable ways, sometimes over years, sometimes over mere weeks. They are temperamental, restless, and prone to outbursts. A particular class of these objects is so notorious for this behavior that astronomers have given them a special name. They are called luminous blue variables, and they represent some of the most unstable stars known to exist. A luminous blue variable can sit quietly for years and then suddenly erupt, throwing off a vast shell of gas in a paroxysm of activity, brightening dramatically before settling back down, as though the star itself is convulsing under the strain of its own brilliance. The most spectacular example of this kind of eruption that we have ever witnessed involves the colossal star system known as Eta Carinae, which I mentioned earlier. In the 1840s, this star did something extraordinary. Over the course of a few years, it suddenly and dramatically brightened until it became one of the most brilliant stars in the entire southern sky, briefly outshining nearly everything around it. This event is now called the Great Eruption. During this convulsion, the star threw off an almost inconceivable amount of material, perhaps 10 or more solar masses worth of gas, expelled in a single titanic outburst. And here is the astonishing part. The star survived. It did not explode and die. It merely had, in a sense, a near-death experience, a violent spasm in which it shed a huge fraction of its mass, and then, eventually, calmed back down. The material it expelled is still expanding outward today, and when we look at Eta Carinae now, we see it surrounded by two enormous glowing lobes of gas, twin billowing clouds that were blasted off during that eruption nearly 2 centuries ago. It's a frozen snapshot of a star caught in the act of tearing itself apart and somehow living through it. That event tells us something profound about the precarious existence of these stars. They are so close to the edge of stability that they can suffer eruptions powerful enough to shed the mass of several suns, and yet not actually die. They are like a person walking along the rim of a volcano, occasionally stumbling and nearly falling in, only to regain their balance at the last moment. The great eruption of Eta Carinae was exactly such a stumble, a moment when the star's luminosity surged so violently past the limit of stability that it convulsed and flung off a part of itself in a desperate bid to survive. And it's worth remembering that the light from this eruption took a very long time to reach us across the vast gulf of space. So even as we study it, we are watching an event from the deep past, a glimpse of a star's agony frozen in transit across the cosmos. Why do these eruptions happen at all? Why isn't the mass loss simply smooth and steady? The answer lies again in that delicate, perilous balance at the Eddington limit. When a star is sitting right at the edge where radiation pressure nearly equals gravity, even a small change can tip it over. If the star's luminosity surges a little, or if its outer layers become slightly more opaque to radiation so that they absorb light more efficiently, the radiation pressure can suddenly exceed gravity across a large region of the surface. When that happens, that entire region becomes unbound. It is no longer held by gravity, and it lifts off, blasting outward in a great eruption. The star, in effect, briefly exceeds its own limit, loses control of its outer layers, and sheds them violently before settling back into a more stable configuration. These stars are so finely balanced that they are constantly at risk of these convulsions, forever flirting with disaster. There's a subtlety here that makes these stars even more interesting, having to do with the relationship between opacity and the wind. Opacity is just a measure of how effectively material blocks or absorbs radiation. The more opaque the gas, the more light it absorbs, and therefore the harder the radiation pushes on it. In the outer layers of a blue hypergiant, the opacity can change depending on temperature and the state of the atoms there. In certain conditions, the opacity can spike, suddenly making the outer layers far more effective at catching the star's light. And when that happens, the radiation pressure on those layers jumps dramatically, which can trigger or intensify the mass loss. So the star's outer atmosphere is not a passive thing being gently pushed. It is a dynamic, shifting environment where opacity changes can suddenly amplify the force of the radiation and drive sudden surges in the wind. This is part of why these stars are so variable and unpredictable. The interplay between their light and their atmosphere is intricate and prone to instability. Let's step back and appreciate the sheer scale of what this mass loss means for the star over its lifetime. A blue hypergiant might be born with, say, 100 solar masses of material, but because of its furious winds and occasional eruptions, by the time it reaches the later stages of its life, it might have shed a large fraction of that original mass, perhaps losing 20, 30, 40 solar masses or more to space. This dramatically transforms the star. As it strips away its outer hydrogen-rich layers, it exposes the deeper, hotter, heavier interior, the layers where the products of fusion have accumulated. The star can change its appearance, its color, even its fundamental character as it sheds these layers. Some massive stars evolve through a sequence of different states as they lose mass, transitioning from blue hypergiants into other exotic and even more extreme types of stars. Their identity is reshaped by the relentless erosion of their own light. One particularly fascinating endpoint of this stripping process produces a type of star called a Wolf-Rayet star. These are stars that have lost so much of their outer hydrogen envelope to their winds that their bare helium-rich cores are exposed directly to space. A Wolf-Rayet star is, in a sense, the naked inner heart of what was once a much larger star, its outer layers having been completely blown away. And these strip stars have winds so ferocious, so dense and fast, that they make even ordinary hypergiant winds look mild by comparison. A Wolf-Rayet star can shed mass at truly prodigious rates. Surrounded by a thick, opaque outflow of material screaming away from its surface at thousands of kilometers per second. These objects represent the late stages of a massive star's life, when it has been so thoroughly eroded by its own radiation that it has been peeled down to its core, still blazing, still bleeding, still racing toward its inevitable end. It's worth pausing to appreciate just how extraordinary the winds of these stripped stars truly are, because they push the physics of mass loss to its absolute extreme. A Wolf-Rayet star is so luminous, and its surface so exposed and hot, that the radiation streaming off it doesn't merely nudge its outer atmosphere outward. It launches it with such force that the entire surface of the star seems to be perpetually lifting off into space. The wind becomes so dense and so opaque that when we look at one of these stars, we are not even seeing its true surface at all. We are seeing only the thick, glowing outflow of material rushing away from it, a permanent shroud of escaping gas so substantial that it hides the star within. The star has, in effect, wrapped itself in a cocoon of its own departing substance. There's also a strange and revealing behavior in the winds of hot stars that astronomers call stability, and it shows just how delicately these outflows are balanced. The strength and speed of the wind depend sensitively on the temperature and the state of the atoms in the star's outer layers. And at certain critical temperatures, The wind can switch almost abruptly between two very different modes, one faster and thinner, the other slower and far denser. A small change in the star's surface conditions can flip the wind from one state to the other, dramatically altering how much mass the star is losing. It is yet another sign of how these stars live perpetually on a knife's edge, where tiny shifts in conditions produce enormous changes in behavior. This is why the most massive stars can lose such staggering amounts of material as they age, and why the rate of that loss is so difficult to predict. The wind is not a steady, dependable thing. It is a dynamic, shifting, sometimes violent process, responding to every change in the star's tortured surface. And every kilogram of material the star loses to this wind is a kilogram it will never explode with, never use, never reclaim. The relentless erosion sculpts the star, reshapes it, and helps determine the precise nature of the death that awaits it. The brighter the star burns, the more savagely it strips itself, right up until the very end. The material that all these stars blast off into space doesn't simply vanish, by the way. It spreads out into the surrounding region, forming glowing clouds and shells and nebulae of gas, lit up by the intense radiation of the star that expelled it. Some of the most beautiful structures in the cosmos are the expanding shells of gas thrown off by massive, unstable stars. And this expelled material is not just empty hydrogen. As the star ages and fuses heavier elements, and as it dredges some of those elements up toward its surface, the wind carries them out into space. So these stars are actually seeding their surroundings with the heavier elements forged in their interiors, scattering enriched material into the galaxy. In a strange and poetic way, the self-destruction of these brilliant stars is also an act of creation, sowing the raw ingredients from which future stars, planets, and perhaps even life might one day be built. The same brilliance that destroys the star also spreads its substance outward to enrich the cosmos. But let's not lose the central thread amid all this richness. The key point, and the thing that ties everything we've just explored back to what came before, is this. A blue hypergiant is so luminous that its own light becomes a destructive force. The brilliance we admire from afar is, up close, a relentless engine of erosion, stripping the star of its mass, blasting its outer layers into space, driving it through convulsions and eruptions, and accelerating its march toward death. Extreme luminosity, which flows from extreme mass and temperature, produces extreme mass loss. The brighter the star, the harder its light pushes, the faster it sheds itself. There is no way to be this bright without also being torn apart by your own radiance. The light and destruction are one and the same. And this gives us a deeper, fuller picture of why these stars are so doomed, so short-lived, so impossible to sustain. It's not just that they burn their internal fuel too fast, though they certainly do. It's also that they cannot hold themselves together against the pressure of their own light. They are fighting gravity with radiation and losing pieces of themselves in the struggle. A blue hypergiant is, in a very real sense, a star that is too bright to survive. A star whose luminosity has pushed it right to the breaking point of what a star can physically endure. It exists in a state of perpetual crisis, devouring itself from within and dismantling itself from without, sustained only by the precarious, ever-shifting balance between the forces trying to hold it together and the forces trying to blow it apart. There's something almost tragic about it when you stop to consider it. These are the most magnificent stars in the universe. the brightest beacons in the cosmos, objects of staggering power and beauty. And yet, that very magnificence is a curse. They are too brilliant to last, too powerful to be stable, too luminous to keep themselves whole. The qualities that make them extraordinary, the mass, the heat, the blinding light, are the very qualities that doom them to a violent and fleeting existence. They cannot be brilliant and enduring. The universe does not permit it. To shine like a million suns is to pay a terrible price, measured in the relentless loss of one's own substance and the certainty of an early, dramatic end. So now we have assembled nearly the full portrait. We understand what makes a blue hypergiant: the extreme mass, the scorching heat, the unparalleled luminosity. We understand why these stars burn out so fast, the runaway fusion in their crushed and superheated cores. And we understand how their own light tears at them, stripping away their mass in colossal winds and violent eruptions, eroding them from the outside even as fusion consumes them from within. A blue hypergiant is a star living on borrowed time, shedding its very substance into the void, burning through its fuel in a desperate rush, balanced always on the razor's edge of stability. But every star's story has an ending, and for a blue hypergiant, that ending is among the most violent and spectacular events the universe has to offer. Having burned so hard and so fast, having shed so much of itself in its frantic, brilliant life, the star eventually arrives at the moment when it can fuse no more. When the furnace finally falters, when the last fuel is spent, the delicate balance that has sustained it through its short, dramatic existence collapses in an instant. And what follows is a catastrophe so immense that, for a brief moment, the dying star can outshine an entire galaxy of billions of ordinary stars combined. The blue hypergiant, having lived fast and burned bright, is destined to die loud in one of the most powerful explosions the cosmos has ever known. And it is to that final, cataclysmic moment that we now turn. We've followed a blue hypergiant through its blazing, desperate life, watching it devour its fuel from within and bleed itself away from without. Now we come to the ending, and to fully appreciate just how dramatic that ending is, we first need to feel in our bones just how short the whole story has been. Because the brevity of these stars is the key to everything, the thread that ties their brilliance to their doom. So let me take a moment to place their fleeting lives against the lives of ordinary stars, side by side, so that the sheer astonishing brevity becomes real to you. And then we'll watch what happens when a star that has lived so fast and so violently finally runs out of road. Consider once more our own sun. It is, to us, the very embodiment of permanence. It has hung in the sky, virtually unchanged, for the entire history of the human species, for the entire history of complex life, for billions of years before any creature looked up to wonder at it. It will continue to shine, steady and reliable, for billions of years to come. The sun has a total fusion lifetime of roughly 10 billion years, and it is presently only about 4.5 billion years into that span, comfortably middle-aged, with vast stretches of stable burning still ahead. From the human perspective, the sun is eternal. Across the whole of recorded history, across every civilization that has ever risen and fallen, it has not visibly changed at all. It is the great constant of our existence. Now set beside it a blue hypergiant with its lifespan of perhaps 2 or 3 million years. The comparison is almost too difficult to hold in the mind. The sun's life is something like 3 or 4,000 times longer than the hypergiants. To put it another way, you could fit the entire life of a blue hypergiant, from its fiery birth to its explosive death, into the time it takes the sun to complete just a tiny sliver of its own existence. If we compress the sun's 10 billion year life into a single year, with its birth on the 1st of January and its death on the following New Year's Eve, then the entire life of a blue hypergiant would last only a few hours of that year. A few hours out of an entire year. The hypergiant would flare into being, blaze with unmatched glory, and snuff itself out before the first day was even over, while the sun went on burning serenely for the remaining 364 days and more. Let me try yet another way of grasping this, because it deserves to land fully. Imagine that the sun's life was scaled down to a single human lifetime of, say, 80 years. A person born when the sun ignited would live their full fourscore years, as the sun lives its 10 billion. On that same scale, where 80 years stands in for 10 billion, the entire life of a blue hypergiant would last only a matter of days. The hypergiant would be born, live its whole brilliant existence, and die, all within the span of a long weekend, while the human-scaled sun lived on for 8 full decades. The hypergiant is a mayfly, dancing brilliantly for a single afternoon. The sun is a great tortoise, plodding steadily across the centuries. They are made of the same fundamental stuff, governed by the same physics, and yet they inhabit utterly different worlds of time, separated by the single fact of mass. And the red dwarfs, the smallest and most modest stars, make the contrast more extreme still. While the hypergiant lives for a few million years and the sun for 10 billion, a red dwarf can shine, faintly but faithfully, for trillions of years, far longer than the current age of the universe itself. So the full span of stellar lifetimes runs from a few million years at the brilliant massive top end to trillions of years at the dim, lightweight bottom end, a range of nearly 1,000,000 to 1. And the deciding factor, the thing that places a star somewhere along this immense spectrum, is its mass. The heavier the star, the hotter its core, the faster it burns, and the shorter its life. The blue hypergiants sit right at the very top, the brightest of all, and therefore inescapably the most fleeting of all. To be the brightest is to be the briefest. This is the iron law that has governed our entire story. So here is a star that has lived its few million years at a frantic, all-consuming pace. It has fused its hydrogen into helium in a furious rush, and then, as its core contracted and heated, it climbed the ladder of heavier fusion, burning helium into carbon, carbon into neon and oxygen, oxygen into silicon, each stage faster than the last, each stage requiring a hotter and more compressed core. We saw in our earlier exploration how these final stages accelerate terrifyingly, the last of them lasting mere months, then days. And now we arrive at the final rung of that ladder, the fusion of silicon into iron, and here the star encounters an obstacle it cannot overcome, a wall built into the very laws of nuclear physics. Throughout its life, the star has survived by a delicate balance. Fusion in the core releases energy, and that energy creates an outward pressure that pushes back against the relentless inward crush of gravity. As long as the core keeps producing energy, it can hold itself up, supporting the enormous weight of the star above it. This is the balance that has sustained the star, in one form or another, through every stage of its existence. But iron is special, and not in a good way. iron is the ash at the bottom of the nuclear fire, the most stable of all atomic nuclei. When you fuse lighter elements together, you release energy. But iron sits at the very bottom of the energy well, and fusing iron into anything heavier does not release energy. It absorbs it. To fuse iron, the star would have to put energy in rather than getting energy out. And so, when the core of a massive star becomes iron, the fire goes out. There is no further fuel to burn, no next rung on the ladder to climb. The energy generation that has held the star up for its entire life suddenly ceases. The outward pressure vanishes. And gravity, which has been waiting, patient and implacable through every moment of the star's existence, finally wins. What happens next is one of the most violent events in the entire universe, and it unfolds with almost incomprehensible speed. The iron core, no longer supported by the outward push of fusion, collapses under its own gravity. And this is not a gentle settling. It is a catastrophic implosion. In a fraction of a second, a core containing more mass than our entire sun, packed into a region perhaps the size of a small planet, collapses inward, crushing down until it is squeezed into an object only a few kilometers across, a sphere of unimaginable density. The core falls inward at a substantial fraction of the speed of light, collapsing in less time than it takes to blink. The matter is compressed so violently that the very atoms are crushed out of existence. The electrons and protons forced together to form neutrons, until the core becomes an almost solid ball of neutron matter. So dense that a single teaspoon of it would weigh billions of tons. And then, having collapsed as far as it can, the core does something remarkable. When it reaches the density of an atomic nucleus, it suddenly becomes incredibly resistant to further compression. The infalling matter, having raced inward at tremendous speed, slams into this newly formed, ultra-rigid neutron core and rebounds, bouncing violently outward. A shockwave is born, a wall of energy and matter blasting outward from the center. And this shockwave, aided by an almost inconceivable flood of ghostly particles called neutrinos that pour out of the collapsing core, tears through the overlying layers of the star and blast them apart. The outer layers of the star, all that material the hypergiant had not yet shed to its winds, are hurled outward into space at thousands of kilometers per second. The star explodes. This is a supernova, one of the most powerful and luminous events the cosmos can produce. The sheer scale of a supernova is almost impossible to convey. For a brief period, days to weeks, a single exploding star can shine with the brilliance of billions of ordinary stars combined. A supernova can briefly outshine the entire galaxy that hosts it. A single dying star blazing as bright as 100 billion suns put together. The energy released in those moments is staggering. More energy than our sun will produce in its entire 10 billion year lifetime, all unleashed in a matter of days. Across the vast distances of intergalactic space, astronomers can see these explosions in galaxies millions or even billions of light years away. Brief, brilliant flares that mark the death of a massive star. When a supernova erupts, it announces the end of a star's life with a flash visible across much of the observable universe. For the blue hypergiant, this explosion is the inevitable consequence of everything we have explored. The star lived fast because its enormous mass forced its core to burn at a furious rate. And because it lived so fast, it arrived at this catastrophic ending so soon. The same mass that made it brilliant is the mass that ensured it would reach an iron core. And an iron core means collapse. And collapse means supernova. The brilliance, the brevity, and the violent death are all aspects of a single underlying cause. They are the mass expressing itself in different ways across the star's short life. A star that shines like a million suns cannot have a quiet, gentle ending. Its very nature demands a spectacular and violent death. To burn so bright is to die loud. The supernova is not merely an ending, though. It is also a profound act of creation and dispersal. And this is one of the most beautiful aspects of the whole story. Throughout its life, the star forged heavier elements in its core: carbon, the oxygen, the silicon, and finally the iron. And in the explosion itself, in the unimaginable heat and pressure of the supernova, even heavier elements are created. Elements that cannot form in the ordinary course of a star's life. Many of the heavier elements in the universe are born in these stellar explosions and in the related collisions of the dense stellar remnants they leave behind. And then the supernova flings all of this material, the products of the star's life and death, outward into space, scattering it across vast regions of the galaxy. This enriched material, seeded with the elements forged in the heart of the dying star, mingles with the clouds of gas and dust that drift through interstellar space. And in time, those clouds collapse to form new stars and new planets. The atoms that were created and dispersed by these dying giants become the raw material for the next generation of stars, and for the worlds that orbit them, and potentially for life itself. The iron in your blood, the calcium in your bones, the oxygen you breathe, much of it was forged in the hearts of massive stars and scattered across space by their deaths. We are, quite literally, made from the ashes of stars that lived and died long before our sun was born. The blue hypergiants, for all their self-destruction, are also among the great creators of the cosmos, enriching the universe with the elements of which everything, including us, is made. Their violent deaths are the soil from which new life can eventually grow. What remains after the explosion depends on just how massive the star was. When the core collapses, it forms one of two kinds of extraordinarily dense remnant. For stars in a certain mass range, the collapsed core stabilizes as a neutron star, that ball of neutron matter only a dozen or so kilometers across, yet containing more mass than the Sun, so dense that its gravity is staggering and its surface conditions are beyond anything we can experience. Some neutron stars spin rapidly and sweep beams of radiation across space like cosmic lighthouses, and we detect their pulses as they flash past the Earth. But for the most massive stars, the blue hypergiants among them, even the neutron core cannot withstand the crushing weight of gravity. The collapse continues, unstoppable, until the matter is crushed down into a single point of infinite density, and a black hole is born. A region of space where gravity is so overwhelming that nothing, not even light itself, can escape its grasp. There's a poignant kind of symmetry in this. The blue hypergiant spent its entire life as the brightest object in the sky, pouring out more light than a million suns, a beacon of almost unbearable brilliance. And in its death, it can become a black hole, the darkest object in the universe, a place from which no light can ever emerge. The most luminous star in the cosmos transforms, in its final moment, into the very embodiment of darkness. The star that outshone everything becomes the thing that swallows light entirely. From the most brilliant to the most black, in a single catastrophic instant. There is something almost mythic about that transformation, the way the greatest light gives birth to the deepest dark. I want to dwell for a moment on how the precarious life of the hypergiant connects to this ending, because the whole story hangs together so elegantly. Remember that throughout its life, the blue hypergiant was bleeding away its mass in those colossal winds and violent eruptions, shedding solar masses of material into space. This mass loss is not incidental to the star's death. It actually shapes the kind of death the star will have, and the kind of explosion it produces. A star that has stripped away much of its outer hydrogen envelope before it dies will explode differently from one that retains its outer layers. Some massive stars, having shed so much material that their bare cores are exposed, the Wolf-Rayet stars we met earlier, produce particularly energetic and distinctive explosions when they finally collapse. So the mass loss that defined the star's tumultuous life also helps determine the precise character of its spectacular death. Everything is connected. The winds, the eruptions, the burning, the collapse, all of it flows from that original extreme mass, all of it part of a single unfolding story. In fact, the most extreme of these stars can produce explosions even more powerful than ordinary supernovae. When a truly massive, rapidly spinning star collapses to form a black hole, the process can, under the right conditions, launch tremendous jets of material outward along the star's axis at nearly the speed of light. These jets can punch through the collapsing star and produce a blast of high energy radiation called a gamma ray burst, among the most luminous and violent events known in the entire universe. For a few seconds, a single gamma ray burst can release more energy than our sun will produce across its entire 10 billion year lifetime, focused into narrow beams that blaze across billions of light years of space. These are the death cries of the most massive stars, the final, most extreme expression of the principle that has guided our whole journey. The more massive the star, the more violent its life, and the more cataclysmic its death. And for a rare few stars, the very most massive that the universe can produce, the ending can be stranger and more violent still, through a mechanism so extreme it almost defies belief. In the hearts of these absolute titans, the core grows so hot that the radiation within it becomes powerful enough to spontaneously transform into matter, conjuring pairs of particles directly out of pure energy. This sounds like a curiosity, but its consequences are catastrophic. When the energy turns into matter, it is no longer providing the outward pressure that holds the star up. The support beneath the star's enormous weight suddenly weakens, and the core begins to collapse. But in these most massive stars, that collapse does not lead to a quiet neutron core or a black hole. Instead, the sudden contraction ignites the remaining fuel all at once in a single, uncontrolled, runaway thermonuclear detonation so powerful that it does not merely blow off the star's outer layers. It obliterates the entire star, blasting every last particle of it into space and leaving behind nothing at all. No neutron star, no black hole, nothing but an expanding cloud of debris and the fading light of one of the most violent explosions the cosmos can create. Astronomers call this a pair instability supernova, and it represents the most complete self-destruction a star can undergo. A death so total that the star erases itself from existence entirely. It is the ultimate expression of the principle that has guided our entire journey. The greater the mass, the more violent the life, and the more absolute the ending. The very largest stars do not simply die. They annihilate themselves so thoroughly that they leave no remnant behind to mark where they once blazed. So let us draw together the full arc of this remarkable story, because every piece now fits into a single, coherent picture, beautiful in its inevitability. A blue hypergiant begins its life with an enormous mass, the material of dozens or even 100 suns. That extreme mass crushes its core to extraordinary temperatures, and because the rate of fusion is so violently sensitive to temperature, the core burns its fuel at a furious, runaway pace. This makes the star almost unimaginably luminous, shining with the light of hundreds of thousands or millions of suns, and so hot at the surface that it glows that fierce, beautiful blue. But that same luminosity carries a terrible price. The star burns through its fuel so fast that it can only live for a few million years, a cosmic eye blink. And its brilliance is so intense that its own light tears at its outer layers, stripping away its mass in tremendous winds and convulsive eruptions, eroding it from the outside even as fusion consumes it from within. The star lives on the very edge of stability, too bright to hold itself together, hemorrhaging its substance into space. And then, having burned through every fuel it can, having climbed the entire ladder of fusion in its frantic rush, the star arrives at an iron core that cannot burn. The fire goes out, the support vanishes, and gravity claims its prize. The core collapses in a fraction of a second, and the star detonates in a supernova so brilliant it can briefly outshine an entire galaxy, scattering the elements forged in its heart across the cosmos and leaving behind, at its center, a neutron star or a black hole. The brightest stars in the universe burn out fastest, and they die loudest. Their brilliance and their brevity and their violent end are not separate facts, but a single truth, seen from different angles, all of them flowing inevitably from that original extreme mass and the searing heat it creates. There is a lesson here, I think, that reaches beyond astronomy, a kind of cosmic poetry written into the laws of physics. The blue hypergiants are the most magnificent stars in existence, the most brilliant, the most powerful, the most awe-inspiring, and yet that very magnificence is what dooms them. They cannot be both brilliant and enduring. The universe does not allow it. The steady, modest stars like our sun and the dim, frugal red dwarfs are the ones that live for billions or trillions of years, quietly and patiently. It is the dazzling giants, the ones that blaze with the most glory, that burn out almost as soon as they are born. That is a trade-off woven into the fabric of the cosmos between brilliance and longevity, between the intensity of a life and its length. The hypergiant chooses, or rather is forced by its nature, to live with overwhelming intensity for a fleeting moment, rather than gently for an age. And perhaps that is why these stars hold such a powerful grip on the imagination. They are the universe's reminder that the most spectacular things are often the most fleeting, that brilliance and impermanence are bound together. A blue hypergiant does not last, but for the brief moment that it exists, it shines brighter than almost anything in all of creation, lighting up its corner of the galaxy with a glory that no ordinary star could ever match. It lives fast, burns with unmatched brilliance, and dies in a blaze of cosmic fire, scattering the seeds of new worlds as it goes. There is something magnificent in that. Something that transcends the simple physics of mass and temperature and fusion. These stars live the most intense lives the universe permits, and they pay for that intensity with their brevity, and in their deaths, they give birth to the elements from which new stars, new planets, and perhaps new life will one day arise, It's worth asking what one of these deaths would actually look like to human eyes, because a supernova is not some abstract event hidden in the equations. It is a sight that can be seen, and throughout history, it has been. When a massive star explodes within our own galaxy, it does not appear as some distant, faint smudge. It blazes into view as a brilliant new point of light, where no star had been before, often bright enough to be seen in broad daylight, casting shadows at night, outshining every other star in the sky for weeks or even months before slowly fading away. Imagine looking up one evening and finding a star so brilliant it rivals the moon, a star that simply was not there the night before. That is what it means to witness the death of a giant, and our ancestors did witness exactly this. Across the centuries, astronomers in ancient China, in the Middle East, and elsewhere recorded the sudden appearance of what they called guest stars, brilliant new lights that flared into the heavens and lingered for a time before vanishing. In the year 1054, observers carefully noted a star so bright it remained visible in daylight for weeks. Centuries later, astronomers turned their telescopes to that very spot and found an expanding cloud of glowing debris, the shattered remains of the star that had exploded all those years before, still racing outward across space. They had found the wreckage of a death that human beings had watched with their own eyes, written down, and passed across nearly 1,000 years of history to us. So, the next time you look up at a clear night sky and find one of those rare blue white stars gleaming among the more ordinary points of light, take a moment to consider what you are seeing. You are looking at a star that is living on borrowed time, a star so brilliant that it is consuming itself from within and tearing itself apart from without. A star that was born, in cosmic terms, just moments ago, and that will be gone again in another moment, vanishing in a supernova that will briefly outshine a galaxy. You are seeing one of the universe's great paradoxes made visible, a thing of supreme brilliance and supreme fragility, the brightest and most beautiful of all the stars, and for that very reason, the most doomed. The blue hypergiants burn brightest of all, and they burn out fastest of all. And in that simple, inescapable truth lies one of the deepest and most beautiful lessons the cosmos has to teach. They shine like a million suns, and they pay for that light with their lives.